It's time to talk about this. But it's also been a long week, and at the end of long weeks, it's really easy to fall into that trap of becoming introspective. And I think I'm going to do that. So why don't we start with a thought question? Maybe we can take turns answering this thought question. And the thought question is, who am I? You can go ahead and pause the video and ponder the answer to that question. I'll wait. Okay, I assume you've done that now, so I guess I'll give my answer. Who am I? I don't know. Maybe I, or me, or myself? Is that the answer you were looking for? Maybe you wanted me to introduce myself. If I had to introduce myself, it's a bit late in the course for that. If I had to introduce myself, I might say something like, "Hi, I'm Bill. I teach programming. Apparently I teach programming on the internet now." But really, if I ask myself, who am I don't go around thinking of myself in my own head as Bill. That's the name you call me. And just like when you introduce yourself, you're giving me a name I can call you. But inside your own head, you're probably I, or me, or myself, or something similar to that. Now, it's actually true that as an egomaniac, sometimes I do refer to myself in the third person, but usually in my own head, I'm I, or me, or myself, or in fact, a personal note, I do sort of think of myself more as William outside of my professional engagement as a guy who teaches programming. And so that brings up an interesting point, which is that you experience the world, everybody calls you some name, but it's not really the name that you use for yourself. The name you use reflectively to refer to yourself. It's a convenience that other people have to be able to identify you. And actually, that's the topic of this video, because we've been spending so much time talking about defining classes that allow objects to be complete citizens of the world, with complete control over their own existence. That includes how they are brought into the world, that would be the construction process, how they leave the world, that would be the destruction process, and everything that happens in between. What data is visible, what aspects of the object's personality are private, what they present to the world as their outward personality, how the world can interact with them, and what operations can happen, and when. And so part of that, of giving the object its own place in the world as a first-class citizen, is trying to figure out an answer to that question. When the object asks itself at the end of a long introspective week, when the object asks itself, who am I? What is the answer? And it's a feature that I have deliberately tried to delay discussing. Now, depending on who you ask, this is something that either comes up pretty early when we discuss object-oriented programming or pretty late. And I'm a member of the school of thought that thinks it should come up pretty late, because I feel like notationally, so if we excuse all of the philosophical wrangling that I was just getting into, notationally, it's sort of better to avoid needing this feature unless you really, really need it. So putting it in gratuitously, writing in this feature because it's sort of interesting to use, I think might actually be a little bit sloppy. I prefer to use the notation we've been using so far. And as a result, it actually turns out that because I think it can be a little bit sloppy, all I really have to present it right off the bat is a contrived exercise. So not really something you need to do in practice because the code is sort of irrational. We'll see in the coming few videos rational reasons we'll need this feature. So it is a valuable feature to have, but I think it should be used sparingly, especially in C++. Something similar to this exists in a lot of languages that use object-oriented programming. In C++, the feature is a little bit, it's clouded a bit by sort of odd notation that's a product of historical baggage. And I'll come back to that a little bit later. First, I want to skim over this exercise. So I've got my main function. I'm creating 2 point objects. We've gotten to know the point object pretty well. We've learned that the point object, in fact, made some friends over the course of the week. We've gotten to know the point object pretty well, and this is yet another variation on it. We create 2 point objects. I call a function called printPoint, and it turns out this point class also has a member called .print. Okay, well, that all seems above board. Maybe a bit of redundancy there, but that all seems above board. The reason the exercise is sort of ridiculous is the 2 prompts that we're going to be working through are deliberately sort of bizarre. They are strange. They're things that no sensible person would really ever write. There are ways around these issues that are far easier than the feature we're going to use. But I'm trying to prove a point here. And I'm doing that, of course, with my class point. So I've got this constructor that takes a double called x and a double called y. And the problem is that the goal of the constructor is to initialize my members x and y. And in previous examples, we've called the constructor arguments xval and yval. Okay, so this time, for some reason, I am insisting that you call the arguments actually x and y. And hopefully you can see that is a bit of a problem because the members I'm trying to initialize are also called x and y. The exercise here is below the prompt, so on line 21, not up here, because there would be a way around it up here. On line 21, initialize the members x and y to equal these two things. That's what you have to do. And it says also, don't try any other funny business. So there are a couple of other clever tricks you could come up with here, like adding member functions or something that would work around this problem. What I want to do is use plain old assignment statements on lines 21 and 22 to set the members x and y to equal the arguments that were provided. And I completely acknowledge this is a ridiculous exercise, but I want some easy way of introducing this strange feature, this reflective term that we're going to need. What does an individual point object use to refer to itself? How does it say I or me or myself? Because it doesn't know. A point object doesn't necessarily know that you've decided to call it P or that you've decided to call it Q. We also understand that in a C++ program, one single object can have tons of different names that we use for it. We can call it different things in different circumstances. So for example, the point that I'm calling P in main happens to be called PT when I pass it into the print point function. The same way that you might call me Bill, but other people in my life might call me William. And one person in my life, which is to say myself, calls me myself or I. So on line 21, I want to write assignment statements that set my two members x and y. And hopefully you can see why there's a problem, because I can't just write x equals x, because in the context of my constructor, I have a local variable called x. So x equals x does nothing, basically. It just assigns this value back to itself. What I want to do is to assign, I guess I could write this in sort of symbolic terms, the member x of this object, is set to be equal to the argument called x of this constructor. That's what I want. I want the assignment statement that assigns the argument you just gave me, called x, to the member of the object, also called x. The issue is, in the constructor, the name x will refer to this thing, to this local variable. So how do I get the name of my member, x, without using just the name x, which would be a conflict? And I have an option. Inside of any member function in an object, there is a special identifier that you can use to refer to the current object. And it is the word this. And you can see the editor is already recognizing that this means something significant. So we could write this assignment statement here. And as you can tell, when the name of the feature is this, it's a bit tough to talk about things because every time I use the word this, it sounds like I'm talking about this. So the line that I've highlighted, the present line, assigns the value of the variable x in the current scope to the member of the current object called x. And the feature we're discussing in the video, this is a pointer. Inside of any member function, you can use the term this, and we call it usually the this pointer, and it will have type, in the current context, point star. And yes, that is a C-style pointer. It's weird because we're used to using references in C++, not pointers. The issue is this was added to the language before references were. And so back then all they had were pointers. That's why we have this odd notation, where otherwise we think the reference is the natural currency of C++, and yet we're using a C-style pointer here, which is a bit odd. There are a bunch of technical implications of that that are even stranger, that fortunately we don't need to worry about in this course. So when I use the name this, I am referring to the current object, the whole current object, not just one of its members. And because it's a pointer, I can follow the pointer and then access a particular member. So I can say this arrow x equals x, and that sets the member x of the current object, this object, to be the value x that I was given. Although we should be a bit wary of pointers because we know that pointers can be null or something in C, in the context of C++, if you were in a member function, you may assume that the this pointer is a valid pointer, and therefore you can just use it. There's no need to check if it equals null, because that would certainly create a bit of an identity crisis for the object to discover that itself is equal to null. So if you want to refer to the current object, the entire current object that you're working with, inside of that object, you would use this, the same way that a human being might refer to themselves in English as I, or me, or myself. So that solves one of these two things. Let's try compiling it. And if we run the code, hopefully I can prove here that when I print out the point, so on line 53, when I call print point, there it is, I print out the members of P, which are the members X and Y, and they are 6 and 17. I take that as a way of meaning that the constructor succeeded. The constructor had to set the members X and Y, and apparently it did, because we can see when we print the point out, the members X and Y are equal to 6 and 17. Okay, what's next? The next thing to do, as you can see in main, we call q.print, and then nothing happens. And that's because the print function has not been written yet. And in this example, this is pretty ridiculous, because if we wanted to write a print function, we might just write some output statements, like I would do in print point. For some reason, the exercise is saying you are required to call print point. You are not allowed to print anything in this function. You have to call the print point function. And the reason, it's a contrived exercise, I get it. The reason is to provide another use for the this pointer. So I want to call print point. And I want to pass in the current object, the entire thing, because print point takes an argument of type point. So I need to come up with a way of referring to the current object on line 36. I am inside the point class. The point object is now referring to itself. So what do I do to get an argument of type point on line 36? Well, we know already that the current object refers to itself as this object. Now, we can't just write print point this, and that's one of those issues with C++'s baggage with C-style pointers. Print point this would be incorrect. Let's see what the compiler has to say about it. The compiler's had a very long week as well. So it says, I'm sorry, you gave me point star. It is able to figure out that you can turn the this pointer into a constant if you need it. But it says you tried to pass a point star, a pointer to the object, into a function that requires a point object directly, so the actual point object. And the issue here is that, again, this is a pointer. So if you want to refer to the actual point object, so I guess conceptually we can think about it sort of like this. Here is some point object, and you've called a member function on that point object. You can think of the this pointer as having type point star and existing inside of any member function. So if you're in a member function, you automatically implicitly have a value called this, and it's a pointer to the current point object, whichever object you're working with right now. If I want something of type point, I have to follow that pointer. And recall the notation for that would be a star. So if you ever find yourself needing to refer to the entire current object in C++, you will notice that you usually write star this. So use the this pointer, follow the arrow to get to the current object, which is really clunky. It's odd notation, and it's a product of this sort of baggage that C++ was designed iteratively over a series of different iterations, and that means that the language wasn't put together all at once. Other languages, a language like Java, you would write something like print point of this. You wouldn't need star this because, well, for one thing, Java claims not to have pointers. So we'll try that. And we'll run it, and we can see now when I call a q.print, so I call q.print on line 57, I get to line 36, I call print point with star this, the current object as its argument, and then I get down to line 44, and we can see I am actually eventually calling print point. So finally, we now, I think, are rounding out the object's identity as a real citizen of the world. It can be a small appliance. It now has its own personality. It controls everything about its lifespan, and it now has a way to refer to itself.